Hello and welcome to this video. In this video we're going to be looking at the energy changes that occur in a single oscillation in simple harmonic motion. Okay, so in the last videos we've looked at a definition of simple harmonic motion, we've looked at the graphical analysis of these motions and how we can represent each of those, how we can calculate those using the equations that we had. And now we're going to use those ideas that we came up with in the last video to describe how the energy of the total system is going to change slightly as a full oscillation carries on. Okay, so let's again first start with this pendulum example, since it's the most intuitive. So let's say we start with a pendulum. And this pendulum is just a ball on a string, and we've displaced it by some amplitude A, and we're just going to let it go, and it's going to swing back and forth. Okay. Now, what we're going to say is we need to notice that all of the energy that is present doesn't change. Okay, because the total energy in the system has to always stay the same. In all of the cases, we're imagining that it has no friction, so there's no dissipative forces, so there's no energy loss. And if it's continuing to go back and forth, there must be energy transfer between some types of energy, but the total energy of the system has to always remain constant. So we're saying that we have total energy must be constant. And then we have to think, okay, so what forms of energy are present when we undergo one oscillation with a pendulum? So what we know, if I were to draw this path more curved, we would find that we actually have a change in height from the ground. So if we imagine there's a ground somewhere here, this ball is going to swoop down and it's going to go back up. And so if we're changing our height, we know we must have some sort of gravitational potential energy. So it means that our total energy is going to be partly consistent of potential energies, and then the other part is we know it's actually moving, and if it's moving it has some velocity, it must have some kinetic energy. So this is the kind of idea that our system has to just be made up of the potential energies and the kinetic energies, and at different positions along this path, we'll find that the potential energy will be different and the kinetic energy will be different, but when they sum together, they always have to give you the same value. Now, we can draw a graph to kind of simplify this. So we're going to draw a graph that has the displacement along the bottom. So this is just x. So this is the positive direction of x, and then the y-axis is just going to be the energy. Okay, now I'm going to use some different colors. So I'm going to say that the potential energy is in red, and let's then have the kinetic energy in blue. And we're going to define this system so that we have a positive x, or a positive displacement on this side, and a negative displacement on this side. So that means that when we're at the center, we can say which one of these are we going to have more of. And that means that we're at our lowest point in the path. So we can first think about how our potential energy is going to be. So our potential energy, if we're as low down as possible, we know potential energy due to gravity is mgh. So if h is really, really small, it means that we have a small amount of energy. So we actually have a minimum amount of energy for the potential at that point. Then as soon as we go to either side and we end up at the maximum of either side, we end up having a very large height, or a larger height than if it was at the minimum, and then that means we have more potential energy. So that means either side, when we get to A, we actually have a maximum potential energy at either side. So the way it changes is as you go away from the center, you're actually gaining potential energy. Okay, now we could simply say that that must mean that if these have to sum to be a constant value, surely the kinetic energy is just going to be a reflection of this, but let's prove that in more detail. If we again go to the smallest part, so when x is equal to 0, you can go back to the graphs and prove for yourself that when the displacement is 0, the velocity is actually the biggest that it could possibly be. And if the velocity is the biggest it could possibly be, then the kinetic energy is the biggest it could possibly be. So that reaches a maximum when x is equal to 0. And then we know either side, when it reaches the maximum point here, it stops for a second to change direction. So its kinetic energy falls to a minimum, either side. And so it does end up being an exact reflection of the potential energy. Okay, but the total energy, which we're actually going to put in green, so green is the total energy, all of these points has to stay constant. Okay, between these points, let me try and draw that one a little better. Between these points, the energy has to stay constant. And this is negative amplitude, and this is the amplitude, and this is where your displacement is 0. So 0 in the middle, amplitude either side. And you'll find that this graph is the same for both cases. Okay, so we have a maximum kinetic energy when we pass the equilibrium position, we have minimum at either maximum, and then the opposite for potential energy, we have a minimum at the equilibrium position because we're at the lowest point, and we have a maximum when we're at the amplitudes because we're at the highest point. So it's the same for both types, or both examples, I should say. And by both examples of SHM, I mean the pendulum and mass spring system. However, the mass spring system does have a little bit extra complication. That's purely down to the fact that the potential energy can actually be split into two different forms. So let's have a look at a mass spring system and see how the energy changes in this case. So we have a mass spring system. Now, our mass spring system, we have a single spring, and we're going to attach some mass to it. This mass has a mass m, and we're going to pull the spring down. So actually, if we were to leave it to rest, it would look something like this. Okay, so let's define this point here to be x equals 0, and we've pulled it down. Let's then say that this is a positive direction and this is a negative direction, just to make sure that we get a positive cosine and not a negative cosine for displacement. So we're going to pull it down, and then we're going to let go, and we're going to observe how it bounces up and down. Now we know that these graphs of displacement, velocity and acceleration will be the same in both of these cases. So it means that this graph that we have, the total energy must still be equal to the potential energy plus the kinetic energy. However, this potential energy, like we've just said, can actually split, because not only do we have the gravitational potential energy, so we have GPE, but we also have the elastic potential energy, elastic PE, from the spring itself, because the spring itself can store energy. We learned about that in materials, and so we're saying that as we extend it, since we know that the elastic potential energy is a half F times delta L, as we extend it, the more it extends, the more energy it has. So when we pull it down, it loses gravitational potential energy, but it gains elastic potential energy. Okay, so let's have a look at one complete cycle of this and just show how this will change, and then we'll show that the graph for it will still remain the same. So let's start in position 1. So let's say position 1, let me draw these out more accurately. So let's say that position 1 is where I have a spring, and actually let me say that I've compressed it to begin with. Okay, so I compress it so that this is x equals 0, this is my equilibrium line, and this here is therefore x equals a. This is my maximum point here. Okay, now at position 1 that we've just defined, potential energy is mostly due to gravitational potential energy, since we're at the maximum height that we could possibly be. But we also will have some elastic potential energy because we've compressed this. So even though it's not extended, we still have a change in L, which means if we have a change in L and there's a force present, and the force currently is just the force due to the weight, that must mean there is some elastic potential energy as well. But there is zero kinetic energy at this point, and when it reaches a maximum on either side, whether it's at the top or at the bottom, its kinetic energy has to be 0. Then let's go to position 2. So this is where it will start to extend, and it's going to come down, and actually the mass would now be along here. So let's say we've reached back to the point where x equals 0. So this is the equilibrium position. This is where if we didn't pull it or we didn't compress it and we just left it, this is where it would naturally reside. So this means that our extension, our potential energy in the thing, is actually 0 at this point. So in position 2, we still have some gravitational potential energy, but most of it has now converted. So the GPE and the EP, so the gravitational potential energy and the elastic potential energy, has mostly gone to kinetic energy, because this is when the kinetic energy is going to be a maximum, because this is when x is equal to 0, the same as when a pendulum crosses the lowest point, it has the highest velocity. This is going to have a maximum, so all of this energy has now gone to kinetic energy, or at least all of this energy has gone to kinetic energy. We'll still have some gravitational potential energy left over. Okay. Position 3 then is where we get back to the lowest position. So let's say this is the equilibrium point, this is x equals 0. We're actually going to have something that's extended down to the very bottom. So this is the mass m at x equals a, or minus a. Now position 3, we have we're going to say we have no gravitational potential energy at this point, but we have full elastic potential energy. So the kinetic energy has now transferred to elastic potential energy because this is fully stretched. Now, what you might ask is, how is it possible that we've had two types of potential energy at the top, but then we only have one type at the bottom, but somehow they're still the same? And that's because this force is different in both of these cases. When we're at the top in position 1, the force acting on this spring is entirely due to mg. But when we're at the bottom in point 3, you have this mass here has mg acting on it, but we also now have the restorative force from this spring. The spring will have a force of k times delta L pushing back up. So actually we end up with the resultant force in both positions is the same. So in here, k delta L must actually be equal to 2 mg, okay, for this to work. Okay, but this isn't relevant as long as you know that it's all elastic potential energy down the bottom. There we go. As long as you know it's all elastic potential energy down the bottom, then you know that the potential energy is back to being a maximum when you're at a maximum point. And then the last thing to do is going to be to then say what happens when it comes back up to the top. So I'm going to go straight for the top here and say this is x equals a, and let x equals 0 be here. Now we know that what's going to happen in 4 is that to get to x equals 0, so to move up just to x equals 0, that means that the elastic potential energy is converting into kinetic energy and some gravitational potential energy because you're rising, and this is why at the center here the total energies are going to be the sum of elastic potential and elastic potential and kinetic energy. Sorry, the sum of kinetic energy and gravitational potential energy when x equals 0. So this is to get to x equals 0. Then to get to x equals a, we've actually then got all the kinetic energy is transferred into gravitational potential energy and EP. So we get back to this position here, and then we'll undergo that change. So just to reiterate everything, because that can get a bit confusing. At the top point here, we have the maximum gravitational potential energy, and we also have some elastic potential energy. As soon as it starts to fall, it's obviously going to increase its velocity, so its kinetic energy increases. And when it gets to x equals 0, because we have no longer got any extension, the elastic potential energy is 0. So at the center point, all of its energy is due to the gravitational potential energy and the kinetic energy. As soon as it falls to the bottom, so it gets to the minimum of the amplitude, it then, all of its kinetic energy and gravitational potential energy has fully gone into elastic potential energy. Then when it starts rising back up, its elastic potential changes back into gravitational potential and kinetic, and then when it gets back up to the top, it goes back to being fully gravitational potential and elastic potential. And from that, we can prove that if we were to draw this graph out again of the energy against the displacement, where we're going to say the potential energy is in red. We know the potential energy is going to be a maximum in both sides, even though we have different forms of potential energy. At the bottom, it's purely down to elastic potential. At the top, it's elastic potential and gravitational potential. And we have a minimum in the middle. Even though we have some gravitational potential and kinetic energy, we're going to refer to it as a minimum. So it'll be the same shape. It probably won't go down to 0, but we're going to say that it will for the sake of this video. And then your kinetic energy, when we're at the top, it's 0. So when we have positive maximum, we have 0 kinetic energy. When we have a negative maximum, it's 0 kinetic energy. When we have when we're at equilibrium, so when we're passing through the center, whether we're traveling up or traveling down, we have the maximum kinetic energy. So then we're going to end up with a graph that looks like this, and then we can conclude that your total energy is going to be a constant throughout this whole oscillation, and hence your graphs will look exactly the same. So now we know that how energy changes in both a pendulum and a mass spring system. In the next video, we're going to go through more about pendulums and mass spring systems and try and identify some of the key properties and why these are particularly interesting cases of simple harmonic motion. Thank you for watching.